We know humans and chimpanzees are related, really closely related. Our DNA is shockingly similar. We are each other's closest living relatives in the entire animal kingdom, so it's a simple, logical question. If we share a common ancestor, where is it? Why haven't paleontologists just dug it up, put it in a museum, and said, here it is. This is the creature that was the starting point for both of us. It's a great question, and the answer is complicated. It's not because of some conspiracy or a missing piece of a puzzle that we just haven't found yet. The real reasons are deeper. They have to do with the brutal reality of how fossils are made, the fuzzy nature of what a species even is, and the very shape of evolution itself. We can't find the last common ancestor because finding it is probably impossible. But the search for it tells us almost everything we need to know. Let's start with the most basic problem. Fossils are rare, incredibly, absurdly, mind-bogglingly rare. Most things that die do not become fossils. They just disappear. Think about every animal you've ever seen, every squirrel, every deer, every bird, every bug. When they die, what happens? They get eaten, or they rot. Scavengers pick them apart. Bacteria and fungi break them down. Their bones are scattered by predators or weather. Within a few months or years, there is simply nothing left. The organic material is recycled back into the ecosystem. That's the normal way of things. It's nature's cleanup crew at work. For an animal to become a fossil, a whole series of lucky accidents has to happen. First, the animal has to die in the right place. Not on an open plain where it will be torn apart. It needs to be buried, and it needs to be buried quickly. Maybe it falls into a bog, or gets caught in a mudslide, or drowns in a lake, and its body sinks to the bottom where soft sediment can cover it. This rapid burial is key. It protects the remains from scavengers and the elements. But that's just step one. The environment has to be right. The soil or sediment can't be too acidic, or the bones will dissolve just like the soft tissue. There needs to be a lack of oxygen, which slows down the bacteria that cause decay. Then, over thousands and thousands of years, groundwater, rich in minerals, has to seep into the bones. Slowly, bit by bit, minerals like silica or calcite replace the original organic material of the bone. It's like making a perfect microscopic cast of the original bone, but made of rock. This process is called polymerization. It's what turns bone into a fossil. And the luck doesn't stop there. After all that, the fossil has to survive for millions of years. The rock layer it's in can't be crushed by tectonic plates. It can't be subducted deep into the Earth's mantle and melted. It can't be eroded away by wind and rain. It has to just sit there, locked in stone, waiting. And then, for us to find it, a final bit of luck is needed. The geological forces that buried it have to reverse. The rock has to be lifted up, and the layers above it have to erode away, exposing the fossil at just the right time for a person to walk by and notice it. Think about the odds. The animal had to die in the right spot, be buried quickly, in the right chemical conditions, survive geological chaos for millions of years, and then be revealed on the surface just when we are looking. It's like winning the lottery multiple times in a row. The vast, vast majority of creatures that have ever lived left no trace behind. Not a single bone. The entire fossil record is just a tiny, fragmentary collection of the lucky few. Now, let's apply this problem to our specific search. The last common ancestor of humans and chimps lived somewhere around 6 to 10 million years ago. Genetics gives us that rough window, and it lived in Africa. Where in Africa? Probably in a forest or a woodland environment. Chimpanzees today live in rainforests. Early human ancestors seem to have lived in environments that were a mix of forest and savanna. So the common ancestor likely lived in a similar, probably forested setting. This is a huge problem for us. Tropical rainforests are one of the worst places on Earth to make a fossil. The soil is acidic, it rains a lot, which speeds up decay, the humidity is high, and the sheer abundance of life, from insects to fungi to scavengers, means that anything that dies gets recycled almost immediately. Bones don't last long. The conditions that preserve fossils, like dry deserts or calm lake beds, are the exact opposite of a tropical forest. So, the very place our ancestor most likely lived is a place that actively destroys the evidence. This is why so many of the most famous human ancestor fossils, like Lucy, were found in places like the East African Rift Valley. That area had volcanoes that would spew ash, burying things quickly. It had lakes that would lay down sediment. It was a geologically active area that was good at both burying and later exposing fossils. But, was the common ancestor living there? Maybe. Or maybe it lived 1,000 miles away in the Congo Basin, an area that is today a vast, dense rainforest where the ground is a fossil-making dead zone. We might be looking at one of the few places where fossils can be found, while the main population of our ancestors lived somewhere else entirely, a place that will never give up its secrets. The geology is working against us, the climate is working against us, and time is working against us. So the first big reason we can't find the last common ancestor is simply that the odds are stacked against us. It may never have fossilized in the first place, and if it did, the fossil is likely still buried under miles of rock or has long since been eroded into dust. We are looking for a needle in a geological haystack, and the needle was probably destroyed millions of years ago. But let's say we get lucky. Let's say a paleontologist is hiking in Ethiopia and stumbles upon a perfect, complete skeleton from 8 million years ago. It has features that look a bit like a chimp and a bit like a human ancestor. How would we know if it was the last common ancestor? This brings us to the second, more complicated problem. The very idea of a single last common ancestor is a bit misleading. We tend to think of it as a single person, a sort of evolutionary atom. But that's not how evolution works. We aren't looking for an individual, we are looking for a fossil from a particular population of animals. The last common ancestor wasn't one creature, it was a species, a group of interbreeding animals that lived and died, spread across a landscape. When we talk about a common ancestor, what we really mean is the last ancestral species before the split. This species was breeding, living its life. Then, over time, maybe a part of its population got separated. Perhaps a river changed course, or a mountain range rose up. One group went down one evolutionary path, and the other group went down another. One path eventually led to chimpanzees and bonobos. The other path eventually led to us. The split itself wasn't a clean, sudden event. It was almost certainly a long, messy process. For thousands, maybe even hundreds of thousands of years, the two diverging populations might have even come back into contact and interbred from time to time. Genetics suggests this might have happened. The initial split was fuzzy. It wasn't like one day a mother from the ancestral species gave birth to two children, and one was the first chimp and the other was the first human. That's a cartoon version of evolution. The reality is a slow, gradual divergence. Imagine a single population. Over generations, the ones living in the east of their range develop slightly different traits from the ones in the west. They can still interbreed, but they are starting to look and act a little different. Over 1,000 more generations, the differences become more pronounced. Eventually, after a very long time, they become so different that they can no longer successfully interbreed. At that point, we can say they are two separate species. So where in that long, blurry process was the last common ancestor? Was it the population just before the split began, or the population during the messy middle when they were still occasionally interbreeding? There is no single moment. There is no clear dividing line. Speciation is a process, not an event. It's like trying to find the exact moment a color blue becomes green as it fades along a spectrum. You can point to a spot that is definitely blue and a spot that is definitely green. But the bit in the middle is a fuzzy, indefinable transition. This makes identifying a fossil as the one a fundamentally impossible task. Let's go back to our lucky paleontologist with the perfect skeleton. Let's call this fossil species Proto-Hominid X. It's from the right time period. It has the right mix of features. But is it the common ancestor, or is it a member of the ancestral population that lived just after the split had begun, but before the differences were obvious? Maybe it's on the chimp branch of the family tree, just a tiny step away from the fork. Or maybe it's on our branch of hominin so early that it still looks almost identical to the ancestor. Or maybe it was a cousin, a separate branch that split off from the ancestral line and then went extinct, leaving no descendants. We could never know for sure. Without a time machine and a DNA sample, we can't place that single fossil with perfect certainty. We could say, this fossil is very close to the split. It shows us what the common ancestor probably looked like. But we could never say, this is it, this is the one. The closer we get to the fork in the road, the more similar all the fossils look. The very thing we are looking for is, by its very nature, almost indistinguishable from its immediate descendants and cousins. This brings up another common misunderstanding. People sometimes talk about the missing link. This phrase conjures up an image of a linear chain of evolution, like apes marching in a line and gradually becoming more human. The missing link would be a creature halfway between an ape and a human. But that's not how evolution works either. Well, evolution isn't a ladder, it's a bush. A huge, sprawling bush with thousands of branches. Every branch is a different species. Most of those branches are dead ends, they went extinct. Both humans and chimps are just two twigs on two different branches of this massive bush. We share a branch for a long time, but then about 8 million years ago, that branch splits. The last common ancestor is the node, the point where our branch and the chimp branch diverge. We are not more evolved than chimpanzees. We have both been evolving for the exact same amount of time since that split. We just evolved in different directions, adapting to different pressures and environments. The chimps are not our ancestors, they are our cousins. We share a common grandparent, so to speak. So when we find a fossil, the challenge is to figure out which branch it belongs to. Is it on our branch of hominin? Is it on the chimp branch of panin? Is it on the main branch before the split? Or is it on a completely separate, extinct branch nearby? The term missing link is unhelpful because it implies there's one link to find. In reality, there are thousands of missing links, a whole web of connections and dead ends that we only have a few fossil snapshots of. So even if we found a perfect fossil from the right time and place, the debate would be endless. Scientists would argue for decades about whether it was truly the ancestor, or just an early cousin of either humans or chimps. The evidence in the bones themselves might not be enough to settle the question. What would this creature even have looked like? We can make some educated guesses. For a long time, scientists assumed the common ancestor was probably a lot like a modern chimpanzee. The thinking was that chimps are knuckle walkers who live in trees, and that our ancestors started out like that and then evolved to be bipedal ground dwellers. So the ancestor was just a sort of generic chimp. But recent fossil discoveries have completely challenged that idea. The most important of these is a fossil called Ardipithecus ramidus, or Ardi for short. Ardi lived about 4.4 million years ago, so she is well on the human side of the split. She is one of our ancestors, not the common ancestor, but she tells us a lot. Ardi's skeleton is surprisingly complete, and it's full of surprises. She could walk on two legs, but her feet also had a grasping big toe, meaning she was still very comfortable in the trees. Crucially, her hands and wrists show that she was not a knuckle walker like a chimp or a gorilla. This is a huge deal. If one of our earliest ancestors after the split wasn't a knuckle walker, then it's very unlikely that the common ancestor was either. What this suggests is that knuckle walking, the thing we thought was a primitive trait, might actually be a specialized adaptation that chimps and gorillas evolved after they split from our lineage. Our common ancestor might have been something different altogether. Maybe it was an ape that walked on the flats of its feet in the trees, like some monkeys do, and had a more flexible approach to getting around. This means that both humans and chimps have changed a lot since the split. We didn't evolve from chimps. We both evolved from something else, and that something else might not look as much like a chimp as we once thought. And we do have a few fossil candidates for this ancestral species. They are all fragmentary. They are all controversial, but they give us tantalizing clues. One is called Sahelanthropus chidensis. It was found in Chad in Central Africa, which is interesting because most finds are from East Africa. It dates to about 7 million years ago, right in the sweet spot for the common ancestor. We only have a skull, nicknamed Tumai, and a few other bits. The skull is a strange mix. It has a small, chimp-sized brain, but its teeth are more like a human's. And the most important part is the foramen magnum, the hole at the base of the skull where the spinal cord connects. In apes that walk on four legs, this hole is at the back of the skull. In humans who walk upright, it's at the bottom, directly underneath the skull. Tumai's foramen magnum is positioned underneath. This strongly suggests that it held its head upright and walked on two legs. A 7 million year old bipedal ape, that's astounding. Is Tumai our earliest known human ancestor right after the split? Or could it be the common ancestor itself, a creature that was already experimenting with upright posture? Or is it a member of a different extinct ape lineage that also happened to evolve bipedalism? Scientists are still arguing about it. The evidence is too sparse to be sure. Another candidate is Orrorin tugenensis, found in Kenya and dating to about 6 million years ago. We don't have a skull for this one, but we have some teeth, and most importantly, a femur or thigh bone. The shape of the top of the femur, particularly the femoral neck, is very similar to that of modern humans. It suggests it bore weight in a way consistent with walking on two legs, but its arms and finger bones suggest it was still an expert climber. So here we have another potential biped from right around the time of the split. Is it a hominin? Is it the ancestor? We don't know. These fossils, Tumai and Orrorin, along with Ardi, paint a picture of a very complex time in our evolution. It seems there were a variety of ancient apes, some of which were starting to walk upright while still being at home in the trees. Our lineage came from one of these groups. The chimp lineage came from another. But finding the exact population at the fork in the road is the problem. These fossils are like single frames from a long, complicated movie. They give us clues to the plot, but they don't show us the whole scene. So far, we have talked mostly about bones. But in the last few decades, a powerful new tool has emerged: genetics. We can't get DNA from fossils that are millions of years old. It degrades far too quickly. But we can compare the DNA of living humans and living chimpanzees. This gives us a different kind of window into the past. By comparing our genomes, scientists can see how different we are. They can count up the number of genetic mutations that separate us, and because mutations happen at a roughly constant rate over time, they can use this difference as a molecular clock to estimate how long it's been since we shared a common ancestor. This is how they came up with a 6 to 10 million year window. The fossil hunters now know which rock layers to look in. But genetics tells us more than just the when. It can tell us about the what. Scientists can work backward and reconstruct parts of the ancestral genome. For example, we know that humans have 23 pairs of chromosomes, while chimps, gorillas, and orangutans all have 24. It turns out that our chromosome 2 is actually the result of two smaller ancestral chromosomes fusing together. We can see the evidence in the DNA, we can see the deactivated centromere from one of the original chromosomes, and the telomeres from the ends fused together in the middle. This fusion event happened on the human branch, after we split from the common ancestor. So we know for certain that the common ancestor had 24 pairs of chromosomes, just like a chimp. Genetics can also tell us about the messiness of the split. By looking at different parts of the genome, scientists have found that some parts of our DNA are much more closely related to chimps than others. And some parts of a chimp's DNA are more closely related to us than to other chimps. So, the best explanation for this is that the split wasn't a clean break. The two emerging lineages probably continued to interbreed for a while after they first separated, mixing their genes back and forth before finally going their separate ways for good. This makes the idea of a single last common ancestor population even fuzzier. It was a long goodbye. So, will we ever find it? The answer is almost certainly no. At least we will never find a single fossil skeleton that we can point to and say, with 100% confidence, this is it. The reasons are now clear. First, the fossilization lottery. The creature we are looking for lived in the wrong place at the wrong time to leave good evidence behind. The chances of its bones surviving are astronomically small. Second, the problem of definition. Speciation is a gradual process. There is no clear line between an ancestral species and its two descendant species. It's a blurry transition zone. Any fossil we find from that zone will be fundamentally ambiguous. We can't identify something that has no sharp definition to begin with. Third, the shape of evolution. The family tree is a dense bush. A fossil from that period could be the ancestor, an early chimp, an early human, or an extinct cousin on a side branch. The closer we get to the split, the harder it is to tell them apart. But this shouldn't feel like a failure. The goal of paleontology isn't to find one single trophy fossil that answers everything. The goal is to piece together the story of our past. And every fossil we find, even a fragmentary one, helps us do that. Toomai tells us that bipedalism may be far older than we thought. Artie tells us that our ancestor wasn't a knuckle walker. Each bone is a clue that helps us refine our hypotheses and paint a clearer picture of the world our ancestors inhabited. We may never find the last common ancestor, but we are learning a tremendous amount about it. We know roughly when and where it lived. We have an increasingly clear idea of the kind of world it occupied, a world of shifting forests and savannas full of strange, extinct creatures. We know it was an ape, but one that was different from any ape alive today. It probably spent time in the trees and on the ground. It likely walked in a way that was neither like a chimp nor a modern human. It gave rise to one lineage that became masters of the forest canopy, and another that became masters of walking the earth. We can't find it because it wasn't a single it. It was a population of animals, living and dying, unaware of their momentous place in history. And it was a process of slow, messy, and magnificent unfolding of genetic and environmental change. Not being able to pinpoint a single fossil isn't a weakness in the theory of evolution. It's a consequence of the very way evolution works. The real answer isn't a skeleton in a museum. It's written in the deep branching history of our own DNA and in the rare, precious fragments of bone that the Earth occasionally gives back to us. The search continues, not for a single creature, but for the full story, and that's a much more exciting quest.